Hello, Professor Troll. My name is Abdelbari. I am PhD student from National School of Applied Science, Qunetra. I would like to present my article with my supervisor Abdessalam 8 Madi entitled Bit Error Rate Performance in NOMA Downlink Transmission Using Additive White Gaussian Noise, Rayleigh and Rician Feeding Channel. The first one is introduction. I will give the definition of 5G in the example of multiple access like orthogonal multiple access, orthogonal frequency division multiple access, frequency division multiple access, code division multiple access, time division multiple access, and finally non-orthogonal multiple access, which is the best one. The second is proposed work, which focuses on two users, near and far user. We focus on analyzing the NOMA system model, signal model, and conducting simulation to evaluate capacity, outage probability, and bit error rate in the downlink transmission between near and far user and the bus station. After that, I will give the NOMA system architecture. The third part is result in discussion. I will give the NOMA's performance evaluation respectively in additive white Gaussian noise, Rayleigh feeding channel in such model like capacity, outage probability, and bit error rate, and other feeding channel called Rician. And finally, I will give the conclusion about the advantages of NOMA in downlink transmission with two users and compare between Rayleigh and Rician feeding channel and what is the best one in terms of bit error rate. And I will give the future work about beamforming and how it can affect in terms of spectral efficiency and fairness. For introduction, 5G wireless communication systems has proposed challenges related to network effectiveness, connectivity, latency, and spectral efficiency. In multiple access, NOMA enables simultaneous access to the communication medium. They offers advantages such as higher spectral efficiency, increased connectivity, lower latency, fairness, and robustness compared to OMA. NOMA is considered a feasible solution with the potential to enhance spectral efficiency in 5G wireless network due to NOMA advantages such as capability of the receiver to employ the interference control technique, namely successive interference cancellation like SIC. We present also an evolution of bit error rate performance in NOMA downlink for two users. We also provide a basic NOMA system architecture, additive voice Gaussian noise, which means AWGN, and compare bit error rate for near and far users. And we provide the normal performance analysis in Rayleigh and Rician feeding channel. Feeding channels can be categorized into different types, including Rayleigh feeding channel, which is widely used to model wireless communication scenario where there is no dominant line of sight component, in contrast Rician feeding channel. For the proposed work, this section provides an overview of downlink NOMA, focusing on a two-user system where signals are transmitted using superposition coding and decoded through successive interference cancellation. The system's performance is analyzed by simulating key metrics like capacity, outage probability, and bit error rate under various channel conditions. In this figure, for both users, user 1 and user 2, the channels connecting both users to the bus station respectively should be represented by the channel coefficients H1 and H2. Before user 2 can decode his own signal, he must first conduct SIC. Before the before the application of SIC, user 2 decipher the signal from user 1. When user 1 uses SIC to cancel its signal to decode its signal, user 2 takes advantages of the SNR. For power division, multiplexing is used by NOMA to share time and frequency resource. The bit error rate performance of NOMA will be shown on an additive white Gaussian noise channel. The general design of the fundamental NOMA system is seen in this figure. Next, we can pass in results and discussion. This study utilized MATLAB simulation R2021A to examine the bit error rate performance in NOMA downlink transmission. Aiming to maximize data flow while minimizing errors, the simulation involved two users interacting via channels such as additive white Gaussian noise, Rayleigh and Rician fading channel. In NOMA, different power allocation were tested, with the far user receiving more power for fineness. Results show that near users generally experienced lower bit error rate and outage probability due to stronger signal power, while far users faced more complex challenges due to distance attenuation and signal fading effects. Enormous performance evaluation in additive white Gaussian noise, as seen in this figure where user 2 is located closer to the bus station than the other one is user 1. NOMA operates better. In this figure below, we know the power weight given to user 1, which is the far user is granted greater power weight given to user 2, which is the near user. We can see the progression of the bit error rate for two users with user 2 experiencing a slightly higher bit error rate than user 1, particularly in the low SNR region. Enormous performance evaluation in the Rayleigh fading channel, while multiple indirect paths such as line of sight links, we study the performance to model capacity. In this figure, we illustrate the rate difference based on power allocation and distance between both users. By computing the SNR and considering distinct user goals, increasing transmission power to bring user 1 closer can enhance the capacity for user 2, resulting in an increased overall capacity between the users. Enormous performance to model outage probability. The outage probability in a communication system varies for near and far users. A lower outage probability for near users indicates a higher chance of maintaining a successful connection, while a higher outage probability for far users implies a high likelihood of successful communication. This figure shows our investigation on increasing energy results in reduced outage probability for both users categories, particularly for user 2 demonstrates lower outage likelihood. This suggests that being closer to the bus station reduces the probability of experiencing an outage. Enormous performance to model bit error rate, increasing transmission power generally leads to a lower bit error rate for near users due to stronger received signal power and higher signal to noise ratio. In this figure, we illustrate bit error rate between user 1 and user 2, showing that increasing transmission power results in a decreased bit error rate for user 2, leading to better relative user performance compared to user 1. Now we can pass enormous performance evaluation in the Rician fading channel, when incorporate a line of sight signal component along with scattered multipath components. The Rician parameter K defined as the ratio of power in the dominant path to power in the scattered path. As we can see in this figure, the impact of the Rician factor or parameter k on bit error rate for both users is observed. It is observed that as k increases, the bit error rate decreases rapidly, indicating improved performance. Now we can pass a conclusion about our paper. This study utilized MATLAB simulation Air 2021A to examine the bit error rate performance in Downlink NOMA transmission, aiming to maximize data flow while minimizing errors. The simulation involved two users interacting via channels such as additive voice Gaussian noise, Rayleigh and Rician fade-in channel. In NOMA, different power allocation were tested, with the far user receiving more power for fairness. Results show that near users generally experienced lower bit error rates and outage probability due to stronger signal power, while far users faced more complex challenges due to distance attenuation and signal fading effects. And thank you for your attention.